All right, this week we are going to be investigating Faraday's law and magnetic induction in the lab. And so, as you look through the handout, you'll go through a bit of an introduction on Faraday's law and how a changing magnetic flux produces an EMF, and that EMF is what's responsible for the induced current that's seen in a loop of wire. And so once you're through the introduction, experiment one is going to have you investigate a simulation found here. So you're going to launch that page. And what you're going to find is a bar magnet. Uh, and you have in the space with the bar magnet a coil of wire. This coil of wire connected in series to a light bulb here. And then a voltage meter hooked up across the light bulb so you can measure the voltage across the light bulb uh, in different scenarios. And so uh, the magnet is clickable, free to move around. You can change the orientation of the magnet. You can see that as I switch the poles of the magnet, what I'm doing is changing the magnetic field of that magnet, and some of the magnetic field is actually crossing through this coil. And so as I change that magnet orientation, I'm actually inducing a current in the circuit. So you can actually view the magnetic field lines produced by the magnet. And so you can see as I'm switching these, right, all of those arrows are changing direction, and so that's giving rise to a change in magnetic flux through the loop. Um, you can move the magnet in and out of the loop, and you'll notice that as the magnet moves in and out, the voltage meter deflects to the right or to the left, depending on what's happening with the magnet and whether or not there's an increase or decrease in magnetic flux due to the motion of the magnet. You'll also notice that, of course, if you stop moving the magnet, even though there's a magnetic field still produced by the magnet and there's magnetic flux through the loop or the coils there, that flux isn't changing, and so you end up getting no induced current when the magnet is at rest. And so there's a variety of different actions that you're instructed to perform here as you investigate this simulation, and then you'll be writing down the answers in the handout. The second part of the lab is going to require you to work through a different simulation suite, and this simulation has a magnet that's going to be dropped through a ring of electrons. Now, it's pretty difficult to see what's going on here, so if you just take your mouse and drag on the screen, you can actually rotate the picture. And so here we're looking sort of directly down through the ring of electrons on top of the magnet. That's a good view, but it doesn't actually give you any perspective that the magnet is moving. And so this is the orientation that I typically, or roughly something like this, I like to look at it from. And I think for every experiment that you're going to be doing here, you're going to select the world-EMF setting. And again, there are instructions listed in the handout, but essentially you're going to select the world EMF settings, you're going to pay attention to the instructions, and then you're going to hit play on the simulation. And play in this case means that the magnet's going to drop. And so what's being plotted here on the right is the induced EMF in the ring of electrons as the magnet is moving. So governed by an acceleration due to gravity of 9.81 meters per second squared, this magnet is falling down to this trampoline-like surface and then recoiling off that surface and then bouncing back up all the way to the initial drop height, and then the motion repeats. So you'll be using this second software to answer a variety of questions related to a magnet falling through or moving through a ring of charge. And so there's a variety of questions, and then you're asked to perform an experiment. You are going to, in this segment, exercise 3, you are going to vary the drop height. So if you look in here, if we reset the simulation with this reset button, we reset the simulation, select our simulation or simulation type, you can adjust the drop height just by selecting in this region. So you can either use the slide bar, or you can just directly in here enter a new value. And so for this exercise 3, you're going to use that change in initial height, and then you're going to run the simulation with the initial height being whatever the prescribed values are in that chart. And so you're going to run the simulation, and you're going to let it run for a little bit so you get the peaks. You can see that the EMF, the induced EMF, is peaking. And so you're going to let it run for a little bit, and then you're going to come back to the handout. So you're going to be running this when the initial height is 0.1 through 0.5 meters. Then you're going to record a variety of things: the upward peak, the downward peak, the flat value. You can see there's this offset in the induced EMF when that induced EMF should be 0, but there's some offset, so you're going to have to take that into account. You're going to subtract off the offset from your peaks. You're also going to calculate the speed at which the magnet is moving through the ring of charge based on that initial height. And you've got instructions here on how to do that. So you're going to record all of this data, and then you're going to produce plots in Excel. So refer back to last week's video or previous videos or your previous labs on how to do that. And then you're going to answer questions associated with these, with the plots and the best line linear fits that you adopt using the add a trend line on Excel. Right? And so then there will be a few more questions that you need to answer, and that's pretty much a summary of the lab for this week, investigating Faraday's law and magnetic induction.